Okay, so this video is on conjugate acid-base pairs, Bronstaed and lowry, and using the values of the equilibrium expression to determine the relative strength of several different species in an equilibrium situation. Usually when you have just a weak acid or weak base in water. Okay, but later on we'll find that there's other ways of producing this set of species in a beaker other than adding an acid or a base when we get to that as well. So this is vinegar or acetic acid again, and what I've done is just written down the equilibrium expression again. So you have the aqueous species on the top, these two are the products, and we have this on we have the acetic acid or the vinegar on the bottom, and the water is missing once again because it's liquid, not aqueous. The Bronstaed and lowry say that acids are proton donors, so they give away hydrogens. So as you can see here, this acid, the HCH2H3O2, is turning into this. It's turning into an acetate ion. It's losing its hydrogen. Now make sure you're clear about this. With oxyacids, the hydrogen that's going to be lost is going to be this guy, okay, down here. This is the ionizable hydrogen. So there might be other hydrogens in there, but it's the one that's attached to the oxygen that goes, and that's the carboxyl group on an organic acid. All right, so acids are proton donors and bases are proton acceptors. So if you want to think of this as a process, the vinegar, this guy right here, right, the vinegar right here, is essentially giving its hydrogen to this guy who's turning into this. All right, so this is our acid and this is our base because it's taken the hydrogen from the vinegar. Okay, now you can look at this as a two-way street, if you will, because in the other direction, right, the H3O plus is turning back into that. Now, what we usually do is link these guys in pairs. So and the difference between the pairs is just one hydrogen. So the difference between acetic acid and the acetate is a single hydrogen, right? So the conjugate of an acid, okay, which is a conjugate base. Now, why is this a base? Why is the acetate ion going to be called a conjugate base? Because in the other direction, it's the acceptor. In the other direction, it's putting the hydrogen back on itself and taking it back from the H3O plus. Okay? So you have a conjugate base and its acid, and you have a base, and this is its conjugate acid. The conjugate acid, the acid will always have one more hydrogen ion in it, or proton, than the base in the conjugate pair. So you can always figure out, like, if I say, what is the conjugate, base of, let's say, I don't know, a weird acid. Let's see, this is HOCl. That's an acid. That's hypochlorous acid. What's its conjugate base? It's going to be OCl minus. Okay. If I say what's the conjugate acid of something, I can go back and forth, and the difference is just one hydrogen. This will always be the acid. That'll be the base. That's a very simple thing to handle and deal with. All right, the question is, what is the relative strength of these species? Like, of the two acids, which is the stronger one, which is the stronger base? Well, really good thing to go with that will work through my course and also in organic chemistry is survival of the weakest. Okay, so whatever there's more of in the system, which didn't react to produce something else, is the weak thing. Whatever is, right, so it's survival of the weakest. The strong things react and produce the weak things. So if you look at the value here, the value for this, Ka, okay, is equal to 1.8 times 10 to the minus 5. Again, unitless because it's an equilibrium constant, right? So what you have here, okay, is a lot of denominator and not much numerator, right? Which tells you, okay, that acetic acid is a survivor, which means acetic acid, okay, since the equilibrium point, now we'll say something, we'll talk about the equilibrium point being towards the left or the right. If I say the equilibrium point is to the left, that means we have a lot of new denominator, or a lot of reactants. If I see the equilibrium point is to the right, that means we have a lot of product. So in this case, the equilibrium point is all the way over here, which means these guys are the survivors. Survivors. That's wrong. There's a no there. Okay, and that means that these guys are weak. So in this thing, this is the weakest acid here, and this is the weakest base, because they're the survivors. Okay? Survival of the weakest. Which means if I put these two guys in water, if I were to just somehow add these two guys to water some way, we end up with a lot of these guys over here. These guys on the right don't survive. All right. So the general rule is if you have a Ka value, okay, like this 10 to the minus 5, you can assume that the ones that are on the left, okay, are the weaker and the ones on the right are the stronger. That's the opposite when you have like strong acids. So if I compare this, let's say, hydrochloric acid, whose Ka value is large, that's what it says in the table, okay, plus water, okay, in this particular case, you're going to have lots of Cl minuses and lots of H3O pluses, right? So the Ka here is large, which means you have lots of these guys, and again, it's survival of the weakest. Well, what is there a lot of? These guys. These guys are the weak ones, and these guys over here are the strongest. So H2O is a much stronger base than Cl minus. Now, bases, okay, can be defined in two ways. The traditional way is with a strong base, which is, right, and that's like if something that directly puts hydroxide ions, that's an Arrhenius base. Arrhenius bases produce hydroxides as their only negative ion, and they don't have to ionize, they just dissociate. So they turn into sodium ions and hydroxide ions. And that's how they make it basic, by adding those hydroxides. Weak bases, there's lots of weak bases, but the most common ones are nitrogenous bases. All right? Nitrogenous bases are like ammonia. Okay? And this isn't ammonia, but this is methylamine. You can just imagine this whole CH3 thing, this methyl group that's on this whole thing over here, that's a methyl group, could have just been another H, in which case the whole thing would have just been this, ammonia. But it's this pair of electrons right here, okay, that likes to grab hydrogens from water. Not a lot, because it's relatively weak. So the Kb, we're going to write out a Kb here, but I'm going to, right? So you have this methylamine, which I'm going to put that, I'm going to just literally write out methylamine down here. Methylamine. Okay, so that is your base right there. And when it gets into the water, what it does is it grabs a hydrogen, so it becomes CH3, NH3. Right, so here's our base, and this is its conjugate acid. Why? Because it has one more hydrogen, NH3 instead of NH2, right? So we put that guy on the top, CH3, NH3 on the top, and we also put one other thing on the top, which is where it gets hydrogen from. Got it from the water. This is OH minus. Now this is the thing that we always associate with a base. And so you have this base and its conjugate acid, right? And you have this this acid, and this is its conjugate base. Now for methylamine, the Kb value, right, which gives us an idea of how much there is on the top and the bottom, right? The Kb value for this, for methylamine, is 4.38 times 10 to the minus 4. And so this is really analogous or similar to the behavior of the weak acid, except it's kind of doing the opposite thing. But in terms of how we look at the K function here, the equilibrium expression, we're kind of looking at the same way, right? You've got these acids and bases and their conjugates on the other side, and what you're seeing is this is the survivor, right? Because we have a big denominator and a very small numerator, which means the methylamine is the weak acid. I mean the weak base, sorry. And the water, okay, is going to be the weaker of the two acids. Notice they're always on the same side, right? So when you look at these things, don't get confused. If you've determined which one's your weak base, it's with the weaker of the two acids. Now, one thing you also want to notice is this really important term called amphiprotic or amphoteric. What you've noticed here is in the two things, I'm going to go back here. Here the water is a weak acid, right? And over here, the water is a weak base. Okay, so water can either act as an acid or a base, and we use the term amphiprotic or amphoteric, which sounds a lot like amphibian, which means it can do either thing, one or the other.